Welcome back to The Explainer, everyone. I am absolutely thrilled to have you here today because we are cracking open a total mystery at the very heart of artificial intelligence. We're talking about something called the knowing-using gap. Now, we're going to be digging into a really highly discussed paper from a team of researchers over at HKUST, including Lu Dai, Ziyang Rao, and their colleagues, who basically decided to tackle one of the most frustrating, head-scratching problems that developers face when they try to teach large language models new tricks.
Okay, let's dive into this. We all kind of like to think of AI memory like a standard computer hard drive, right? You put the data in, and boom, it's there to be used. But the reality of how these models actually store and retrieve information is far stranger than that. I mean, have you ever taught someone a new fact, and they repeat it back to you flawlessly? But then when you ask them to actually apply that fact to solve a simple problem, they just stare at you blankly? Well, large language models do the exact same thing. You can fine-tune a model with brand new information. It will successfully memorize that data for sure. But when you ask it to use that injected knowledge in a downstream reasoning task, like say combining it with another fact to reach a conclusion, it completely fails. It is such a bizarre phenomenon. The model absolutely possesses the information, but it is literally incapable of reasoning with it. The researchers formalized this specific failure, and they call it the knowing-using gap. So formally, it's defined as a critical failure in fine-tuning, and it's marked by two main things: an accuracy gap and a temporal lag. Basically, there's this fundamental disconnect between the exact moment a model successfully memorizes a fact and the point at which it can actually generalize that fact to answer a complex question. The knowledge is just stuck in a sort of limbo. And this gap? It's the prime suspect in our ongoing mystery of why fine-tuned knowledge just isn't translating into dynamic, usable reasoning. So how exactly do you go about investigating a suspect that lives entirely inside billions of artificial neurons? Well, the research team came up with a brilliantly clever three-step investigative methodology. Step 1, they fine-tune the LLMs with completely unseen knowledge, basically injecting fresh facts right into the system. Step 2 is where it gets super cool. They monitored the internal spatial permeation dynamics. Now, in plain English, that means they literally peeked inside the AI's hidden layers to watch where this new knowledge was physically moving and settling. And then step 3, they intervened. They didn't just sit back and watch passively, they actively manipulated the network to track exactly how the knowledge was behaving deep inside the architecture.
To actually perform that intervention, they invented a brand new diagnostic tool called self-patching. Think of self-patching as like a microscopic tracking device combined with a teleporter. It allows the researchers to identify specific activation locations within the model. So if a model fails to generalize a fact, self-patching tests what happens if you manually grab the internal representation of that fact and just relocate it to a different part of the network. If moving the data suddenly fixes the generalization failure, well, you've just found exactly where the knowledge was getting stuck in the first place. This was their absolute primary detective tool to map out the bottleneck.
And using this self-patching technique, they finally unmasked the culprit behind the knowing-using gap. The answer is knowledge circuit misalignment. I know, it sounds super technical, but it actually represents a massive breakthrough in mechanistic interpretability. The model isn't deleting the knowledge and it isn't overwriting it. Instead, the internal pathways of the AI itself are fundamentally misaligned. The data is just sitting there in the dark, completely disconnected from the very circuits that were designed to process it.
So the crucial point is exactly how this misalignment breaks down. Let's look at the mechanics really quick. First, the memorized representations do successfully exist internally. The fine-tuning worked. The facts are in the building. Second, however, they're just not routed correctly. And third, because of this poor routing, the knowledge fails to reach the computation-effective layers. Imagine a brilliant employee sitting in a corporate office, and they have the exact solution to a major problem. But all their emails are getting routed to a defunct server instead of the executive board. The knowledge is right there, but because it never actually reaches the computation layers, the model acts as if it's completely ignorant.
Now, what's really wild is the incredible resolution the researchers achieved here. Once they understood that this was essentially a routing issue, a knowledge circuit misalignment, they designed a surprisingly simple heuristic strategy to fix it. And it worked beautifully. Across several different domains, which really proved the robustness of their findings, this strategy successfully recovered between 58 and 75% of the oracle headroom. What that means is they closed up to 75% of the total possible performance gap in those failed generalization cases. By basically forcing the knowledge to route to the correct computation-effective layers, they dramatically bridge that knowing-using gap.
But as we all know, science doesn't just stop at publication, especially not in the open-source AI community. So let's shift gears and look at how this builds into an incredible discussion over on the Hugging Face forum, which I like to call the Community Interrogation Room. A user named Libok Suak read through the paper and raised some incredibly sharp, fascinating questions. You see, the researchers primarily tested Quen 2.5 and Llama 3 Docs models, and Libok Suak really wanted to challenge generality of these findings, asking specifically how this applies to modern, natively reasoning-oriented models. Libok Suak pointed out this glaring contrast between in-context learning and fine-tuning. If you give a strong recent model previously unseen supporting facts directly in the text prompt, which is in-context learning, the model can easily perform really reliable multi-hop reasoning. It pieces the clues together perfectly. Yet, as the paper shows, if you inject those exact same facts via fine-tuning, the model suddenly struggles to verbalize and generalize them. Libok Suak argued that this proves multi-hop composition itself isn't the bottleneck. The model can reason, so why on earth does fine-tuning specifically break this ability?
And this brilliantly illustrates the fundamental difference in how machines actually remember, which the paper's author, Lu Dai, stepped into the forum to explain. Lu Dai points out that we are way too used to standard computers, the von Neumann architecture, where storage memory is completely separated from the computing processor. You fetch a file, you process it. Simple. But AI memory does not work that way at all. Language models don't have a separated storage address. Instead, they generalize injected knowledge based on the kernel similarity of the training query and the test query. In other words, it retrieves information based on how similar the current question feels to its past training, rather than looking up a specific hard drive address. The memory and the compute are completely tangled together in this massive web of similarities.
Lu Dai goes on to explain exactly why this makes fine-tuning so incredibly fragile. While in-context learning is super easy and pre-training is really robust, vanilla fine-tuning is brittle. Because of this heavy reliance on kernel similarity, models end up failing to verbalize reasoning hops even when they can answer each individual hop correctly on its own. And it gets worse. When you try to force the model to think using chain of thought prompting, it actually backfires. The model often drifts away from the fine-tuned facts entirely, defaulting to its prior knowledge, or it just simply hallucinates an answer instead of actually following the correct reasoning chain.
This entire debate culminated in one of the most profound summaries of AI mechanics I have seen in a long time, dropped into the forum by a user named Whiskers Whisper. Let's just take a second to really let this sink in. Language models don't explicitly store raw knowledge, they store analogies to reasoning trees. Wow. It just completely shifts how we need to think about these systems. You aren't just saving a text file into the model's weights, you are literally bending its internal reasoning trees, which is exactly why that knowledge circuit misalignment happens in the very first place. Which brings us to the ultimate question for all of you focused learners and builders out there. We now know that the knowing-using gap is real. We know it's caused by internal circuits misaligning fine-tuned facts right away from the computational layers. And we know that AI memory is way less of a filing cabinet and much more of a complex web of reasoning analogies. So, armed with this cutting-edge mechanistic interpretability, I want to challenge you to look at your own work. If knowledge is just an analogy to a reasoning tree, how are you going to bridge the knowing-using gap in your next open-source AI model? Thank you so much for joining me on this explainer, and honestly, I cannot wait to see what you all build with these insights.